Today, we're happy to have Nitya here, who will tell us about Turán problems in directed and mixed graphs. And how do you like people to ask questions?
I think people can feel free to ask questions whenever during the talk, but I can't see very well because I'm seeing the slides of Simon. If you just shout or something if people ask questions, I'm happy to answer them whenever as we go.
Okay, yeah, I can relay them. Okay, so go ahead.
Perfect. So, like Simon said, my name is Nitya. Maybe I'll just briefly introduce myself. So, I now work at Jane Street. I did my undergrad at Stanford and my PhD at MIT. I wrote my first ever math paper with Simon in 2015, which
made my first date maybe 5, 6 days.
um, was there an audio problem or are we good?
Yeah, someone was just accidentally unmuted.
All right, cool. I wrote my first ever math paper with Simon in 2015, which is now 10 years ago, which is a very long time ago. And today I'm going to talk about a problem that's been pretty close to my heart for the last several years, sharing a little bit of new results, but mostly kind of telling a story of a problem that we have thought about and understood very, very well, and a very similar problem that is, I think, equally interesting that we have thought about and understood far more poorly. So I will share some results, but I think mostly this talk will have a lot of open problems that I think are really exciting and maybe surprisingly tractable relative to the landscape of other open problems in this and related areas. Okay, so to maybe get started, the area I'm going to talk about today is extremal graph theory, which I'll give a brief introduction to. So extremal combinatorics is an area of combinatorics as a whole, where we're trying to understand how big or how small some function of a combinatorial object can be given certain restrictions. Now, this kind of sounds pretty vague, so maybe we'll immediately jump into the specific application of this kind of question that we'll study today, which is a problem or a class of problems on graphs. So a graph is like some object that has a vertex set or a set of points V and an edge set E of some pairs of vertices. Okay? We'll say that some H is a subgraph of G if we can form it by deleting vertices and edges from G. So maybe just as an example, we have this graph G, which is a triangle, and we have these two examples of subgraphs, which are just subsets of vertices and edges, right? There's no rule that we have to take all possible edges once we take a vertex subset. So this is kind of the starting point. And I think a very common kind of question that we ask in extremal graph theory, in fact, the field originated with one such question, which is Mantel's theorem. And Mantel's theorem asks the following question. It says, suppose I have a graph which has n vertices, and this graph has no triangles. How many edges can I possibly stuff into this graph? And the answer is you can stuff in n squared over 4 edges. I'm not going to be careful about odd and even numbers. And the way that you do that is you put n over 2 vertices on the left and n over 2 vertices on the right, and you connect all the left and right vertices. Now, this has no triangles. In fact, it has no cycles or loops that have odd length, and it has n squared over 4 edges. And it turns out that you can't do any better. There are many different nice arguments that show this, but this was kind of generalized by Turán, which maybe started the field of Turán problems, with Turán's theorem. And Turán's theorem generalizes this question of how big, how many edges can we put in a graph without, there appearing some forbidden substructure. In Mantel's theorem, it was a triangle, and in the case of Turán's theorem, it's an R-clique, which are R vertices that are formed by connecting all the pairs of distinct vertices. All right? I guess relatedly, we'll say that a graph is R-partite if I can group up the vertices into R pieces so that all edges are between distinct pieces. Okay, and maybe to make one more definition, we'll say that the Turán graph is the complete balanced R-partite graph on n vertices, and I think these are all better illustrated via pictures. So you can see on the left, we have a figure, which is a clique with 7 vertices. So these are 7 points, and we connect every single pair of points. And on the right, we have the Turán graph, which has 13 vertices, and it's 4-partite. So I think this is the right way to visualize a graph being R-partite, which is we have R groups, and it's a complete R-partite graph because whenever 2 vertices are in different groups, we've connected them by an edge. And we call this the Turán graph because it's balanced, because every group has as equal as possible many vertices as every other group, right? Maybe it's not divisible by 4, but we do kind of the best we can. And what
Wait,
Turán's
wait. How do we know Turing graphs exist, and R graphs for all? Do they exist for all and R?
Yes, because we just do our best to balance. So that
Oh,
we might
okay.
not be able to perfectly balance. You can see here that we have 4 vertices in one part and 3 in all the other parts. So
Yeah.
balance just means as equal as possible subject to
Okay.
constraints about
Oh,
integers.
okay. I see.
Yes, other questions? And what Turán's theorem says is it says something very beautiful and I think quite nicely generalizes Mantel's theorem. So a different way to recast Mantel's theorem is to say, how do I prevent a triangle from appearing in a graph? Well, I take like a big blow up of something that looks like an edge. Like I take a single edge and I stick like a bunch of vertices on the left end point of the edge and a bunch of vertices on the right end point of the edge, and I connect those. And Turán's theorem is like exactly that generalization, where Turán's theorem says that to avoid a clique on our vertices, so for example, to avoid this clique on 7 vertices, what I should do is I should make 6 parts, connect every pair of vertices that are in different parts, every pair of vertices in like different parts, and I should like kind of do this in the densest possible way, which is to make all of the parts as equal as possible and to connect every pair I possibly can. And so, kind of Turán's theorem, as I've written it here, it gives you some upper bound on how many edges it's possible for a KR-free graph to have. But I think kind of one important thing about Turán's theorem and extremal graph theory in general is, the upper bound is very nice and all that. But one of the things that's the most interesting about this upper bound is that it tells us something structural. We're not just saying, oh, the densest graph has like this many edges and who knows what it is. We're saying the densest graph, in fact, is obtained by this very particular natural construction. So the way that what Turán theorem did to prove this upper bound is he showed that, in fact, explicitly, this kind of multi-partite graph in some robust sense is like the unique way to maximize the number of edges if you forbid a clique. So like the best thing I can do if I don't want a K7 to appear is to take my vertices, divide them into 6 equal groups and connect all the pairs of vertices in different groups. And this is like true in a really, really quite robust sense, which is that if you're like near, having the most number of edges you can without having a K7, in fact, you are also like near this 6-partite construction. So I think this is really beautiful, and this highlights one of the reasons we care a lot about extremal graph theory, because we often learn things about the structure of objects by studying what the extreme examples are. We can also learn things about what the typical structure of objects are. And I think a different way to say this is that, triangle-free graphs like to be bipartite. They like to be kind of free of odd cycles. That's like a thing that we learn. Okay. So, why stop at cliques? I guess you can generalize this to ask the same question about any other graph. And so we'll generalize this by defining a notion called the extremal number. So the extremal number is a function that takes 2 parameters. The first is n, which is the number of vertices in the graph. Throughout this talk, n will always be the number of vertices, and you should think of it as a very, very, very large number going to infinity. And f, you should think of as some small fixed structure, like a triangle, that we forbid from appearing in the graph. And so the kinds of questions we're going to be concerned with are how many edges can we put into an n-vertex graph asymptotically without, some copy of f appearing. At some point, no matter how hard we try, a copy of f will appear somewhere in the graph. And the question is
there's a question in the chat. Is a graph without r cliques always r-partite?
That is not true. So that is a great question. And a way to see this is you can, if you draw a pentagon that doesn't have any triangles in it, but it is not r-partite. And the way you can see that is not r-partite is if you try and put vertices into groups, 2 groups, you can call them the red group and the blue group. You need to only have edges between red and blue vertices, and you can't do that because you have an odd number of vertices in a pentagon. And in fact, like I gave an example, but this can get arbitrarily bad. So there's no guarantee that it will be r-partite. However, a different quantitative statement is true, which is that most graphs that are free of r-cliques are r-partite or close to r-partite, I should say. So something kind of maybe more quantitative is kind of true in a weaker sense, but the strict statement is not true. Other questions? Cool. So like I said, we're going to kind of bravely proceed and try and ask the same question. So this is really like, I'm talking about these theorems, but these theorems in the 1900s really laid the foundation for the whole field of extremal graph theory and extremal combinatorics, which is a really big area of math. And in order to measure this, in order to kind of study the extremal number of a graph, we need like some replacement for the number r, right? So if I have a KR-free graph, the number r played like a key role because we wanted, the extremal construction to be the complete balanced r-1 partite graph. And the number that's going to replace r, the role that r has for cliques, for general subgraphs that we forbid, is the chromatic number. And this is just kind of measuring the partiteness of a graph f. What do I mean by that? So if I have a graph f, the chromatic number is like the minimum number of colors I need. And you can think of these as like groups I need to partition into, so that if I take, neighboring vertices, they're in different groups. So a different way to kind of for me to English, the definition of chromatic number is the chromatic number of a graph F is like the smallest value R, so that F is R partite. Like there's a way for me to divide F up into R groups so that all of the edges go between parts, different parts. Does that kind of make sense to folks? And what Erdős Stone and Simonovits showed in 1946 is that in fact Turán's theorem kind of substituting, R for the chromatic number exactly holds, which is that the extremal number of an F-free graph, so like kind of how many edges I can put into a graph without making a copy of F, is exactly by taking, an R-partite graph, where R is the chromatic number of F minus 1, and making it a balanced blow-up. So they in fact showed like literally the same construction that's true for Turán's theorem is true for, a general forbidden graph. It's just that like to decide how many parts you have, you take like how many parts you need in order to fit F in without having edges inside a part, and you subtract 1. Does that make sense to folks? Do people have any questions about this theorem? So in extremal graph theory, we're often interested in kind of getting answers that are asymptotically correct. So you'll see that there's a bunch of little o1s here, which means that there's some lower order term. So you can think of it as 1 minus 1 over the chromatic number minus 1 times n squared over 2, plus some quantity that is like n to some power that is like less than 2. This is a good way to think about things. For example, we're not like very concerned about the difference between n choose 2 and n squared over 2. You can see like actually I should put n choose 2 there, and we're not very concerned about that because that difference is lower order. And if I take, some graph F, the Erdős Stone Simonovits theorem basically answers the question, asymptotically for, how many edges I can put into a graph while keeping it F-free. And it answers it for almost all graphs. There's one kind of notable exception, though, of a family of graphs where the Erdős Stone Simonovits theorem will not give me an asymptotic answer. Can like anyone tell me or call out like kind of where this will not give me an asymptotically tight answer?
Number is 1.
If the chromatic number is 1, I agree, that's true. So the chromatic number is 1, however, then, there's not that many the graph can't have any edges. So maybe that's not very interesting because the answer there is like 0. Like once you put any edge in, your chromatic number is at least 2. Can anyone tell me another case?
When it's 2?
Exactly. When the chromatic number of this graph, of a graph F is 2, which it is for lots of interesting graphs, for example, for any even length cycle, if you like draw a square or a hexagon, those all have chromatic number 2. You can see if we plug into this formula, we get that the extremal number is like 0 plus little o1 times n squared over 2. All that just means is that you can put like asymptotically fewer than n squared edges into the graph. Like maybe we can only put in like n to the 4/3 number of edges, or n to the 5/3 number of edges, or n to the 15 over 8, a number of edges in the graph asymptotically. But we don't distinguish between any of those possible options. We just say that it's like, n to some exponent that's less than 2. In fact, that's not even what little o means, but I'm being a little bit sloppy here because that's in fact true for this problem. That it's like n to some rational number, it's upper bounded by n to some rational number that's strictly less than 2. And
let's say the chromatic number is 2, right?
Yeah.
The construction that Erdős showed, like with the maximal graph, like that has the graph that has a maximal number of edges, like isn't that still like the optimal construction?
Well, no, the Erdős Stone Simonovits construction won't tell you anything, right? Because think about what the construction is. Because our big plan was we take, chromatic number is 2. So let's say the chromatic number is 3. Then we subtract 1, we get 2, and we take a 2-partite graph and connect all the parts. That strategy doesn't really work when you have a chromatic number 2, because you subtract 1 and you get 1. And then a 1-partite graph is just like a blob with no edges. So that's in fact the construction, the Turán construction, just gives you a blob with no edges. And what this theorem tells you is that up to, epsilon times n squared, having no edges at all is right, which is true, but is not very illuminating. Other questions? All right, so this is like not very satisfying. So we do want a construction, and we do want to understand kind of what we can say about how dense a graph can be, for example, without having any squares up here. And it turns out that this is like a really rich area, and in fact, there's a lot of really open questions, despite the fact that whenever the chromatic number is bigger than 2, we basically exactly understood everything there is to know about the problem. Oh, why has my slides decided to advance here? All right, one moment. let's see. My slides have decided to advance to 100, which is a little bit of an interesting choice, but never fear, we can. Great. All right, we've returned back to where we were. So like we discussed, the Erdős Stone Simonovits theorem gives us the right answer asymptotically if the chromatic number is at least 3. And when the chromatic number is 2, we just learned that it's like less than epsilon times n squared edges, which is not very illuminating. And understanding this maximum density is still open for general F. And in fact, knowing what the asymptotic density is open for like really all but like a very small list of F. All right. But to tell you a little bit about what we do know about this problem, let me kind of recall the complete bipartite graphs. So the complete bipartite graph KST here is just saying I have S vertices on the left, I have T vertices on the right, and then I connect all of the pairs of vertices in different parts. So this graph here is bipartite. It has chromatic number 2 because I can color S red and T blue, and then all of my edges have exactly one red and one blue endpoint. And in 1954, Kaleidoscope and Turán showed an upper bound. They showed that the extremal number of this complete bipartite graph is upper bounded by n to the 2 minus 1 over s. And, you can pick your favorite side to be s. So this, you can take like, the appropriate side to get the strongest possible upper bound. And this is really illuminating because this tells us that in general, we have some upper bound for any bipartite graph on its extremal number of the form n to the 2 minus 1 over something. And why is that the case? Well, if I have one of these KSTs up here, then if I have any bipartite graph where like, both parts, have size less than or equal to s and t, let's say I have a bipartite graph with t vertices, then if I have, a KTT in my graph, I certainly have that bipartite graph with t vertices appearing as a subgraph of the KTT, right? So I can't have like, as soon as I get a KTT, I get all of the bipartite subgraphs that have at most t vertices. And so what this tells me is this gives me an upper bound for any bipartite graph. This upper bound is not necessarily tight, but it is better than like between 0 and epsilon n squared edges. So the story for upper bounds, is really nice. The story for lower bounds is like not so exciting. So for K22, which is just a square drawn a little funnily, we know exactly the right answer. And this is like comes from a geometric construction that matches the Kaleidoscope-Turán upper bound. We also know what the right answer is for K33, which is also a geometric construction that also, kind of matches the Kaleidoscope-Turán upper bound. And there's a conjecture that this kind of continues to be true for complete bipartite graphs, but this is in fact still open. And there's kind of lots of progress that's made on a variety of different axes, but understanding Turán numbers of complete bipartite graphs is like quite hard and is a very active area of research with lots of exciting recent developments and lots of progress being made, where a lot of ground still remains, broadly, widely open. Maybe to just highlight one further example, if I have a length 2k cycle, like a square, a hexagon, an octagon, Bondi and Simonovits showed a much stronger upper bound, right? They showed that, because naively, I would get like n to the 2 minus 1 over k. But they showed that in fact, you will get a cycle appearing very quickly in your graph as soon as you have at least n to the 1 plus 1 over k edges. And this is known to be tight for a grand total of 3 examples of cycles, one of which was overlapping with an example I stated earlier. And it's also believed to be true in general, but not known. So this is like an example of how little we know about what seems to be like very similar to a problem that we fully understood in the early 1900s. Now, there's been like a really large amount of research and effort that has gone into studying these extremal numbers of bipartite graphs. And I think there's lots of exciting problems to work on and progress to work on, and these questions tend to be quite difficult, and the constructions also tend to come from a variety of geometric places and also be very interesting. So I'm happy to talk more about those, kind of offline, but I'm planning to now switch my attention to kind of another very related Turán problem that I think is equally interesting, where far less is understood, across a variety of different subgraph types. Before I do so, does anyone have any questions about anything I've discussed so far? All right. So we're going to now turn our attention to graphs that have orientations. So, the motivation for studying graphs comes from a wide variety of places, but typically we think of graphs as undirected, where, we have some vertices and we have some edges, which are just pairs of vertices. But a lot of natural examples of graphs and networks have some natural orientation or structure to them. For example, you can make kind of graphs where, different teams play each other in a sports league, and you can draw arrows between the teams that lose to the teams that win. You can think of traffic networks or communication networks where there is some inherent notion of direction. And so oriented graphs and directed graphs, which are two different sets of objects, and I will discuss both of them, kind of try to capture these sorts of effects. So an oriented graph is just a collection of edges, a collection of vertices, and a collection of edges, and an edge goes from one vertex to another. But in an oriented graph, I'm not permitted to have multiple edges between the same set of vertices. So you can think of the way I get an oriented graph is that I start with a regular undirected graph, and I draw some arrows on the edges. But I don't ever put like two edges between the same pair of vertices. A particular kind of oriented graph that's very useful to think about, that kind of stands in for cliques, are transitive tournaments. So a transitive tournament is just, it's a complete oriented graph on 8 vertices. So every single pair of vertices is connected to each other. And there's some labeling I can put on the vertices, 1 to 8, where all of the edges are pointed from lower numbers to higher numbers. So you can see here that all of the edges should go, hopefully, if I drew my Tixie right, from smaller numbers to bigger numbers. And so, with this setup, we can ask the same questions that we asked earlier, which is if I have an oriented graph F, how many edges can I put in, if I have an oriented graph, how many edges can I put in without getting a copy of some bad, forbidden oriented graph F? This is like a very natural question that you can ask. So one kind of, natural place to start is, suppose my forbidden structure has a directed cycle. So it has like a loop that I can follow by following the arrows. Then, if I look at any transitive tournament, I have no loops by following the arrows because all of the edges go from small numbers to bigger numbers, right? So if I have a loop, it must necessarily at some point contain an edge that goes from a big number to a small number and an edge from a small number to a big number. And thus, transitive tournaments do not contain any subgraphs that have directed loops. Oh, so what that means is maybe something very boring, which is that if, I'm trying to forbid some, oriented graph that has a directed cycle, then in fact, I can put in as many edges as humanly possible. I can put in all n choose 2 edges as long as I orient them in a transitive orientation, right? Where edges go from small numbers to big numbers with some labeling. And so maybe this is not a very interesting problem.
There's a question. Is the tensor product of transitive tournaments also transitive?
Well, I think the answer is no. It depends on, I guess, what kind of tensor product you define. But I think that also depends on your definition of transitive. So for transitive tournament, there's a unique definition of how we define transitivity. And what do I mean by that? In that every pair of vertices is already connected by some edge. And so we just require that edge to go in the right direction. Whereas there are two different notions of transitivity for general directed graphs. The first is that, if I have let's suppose I have an edge from A to B and from B to C, then if there is an edge between A and C, it has to go A to C. That's one notion. The second is that there should be an edge that, if I have A to B and B to C, I should have some edge, A to C, like kind of requiring the tournament structure. And so one of these is true and one of them is not. I think you have to be careful though, because these kind of blow up kind of constructions typically do not work for oriented graphs. Other questions with the definitions? Cool. So in order for this Turán problem to be interesting,
I'm really sorry to interrupt.
No,
Could you
please do.
go over the definition of the oriented transitive graph once again?
Yes. An oriented transitive graph is just a graph. It's like a way to think about it is that an oriented transitive graph is just a subgraph of some transitive tournament. If I tell you that that an oriented graph is transitive, what that means is that there's some way for me to number the vertices of the graph so that all of the edges go from small numbers to big numbers. So this
Okay,
is like
okay,
not
thank you so
possible if
much.
you have like edges going around in a loop, for example.
Okay, thanks.
Other questions? And these are great questions. It's good to stop me and ask questions now before I spend the next like 30 minutes discussing oriented and directed graphs. All right. So in order for this problem to be interesting, we're going to require that our graphs that we're forbidding do not actually have any cycles in them. Otherwise, the problem is not very interesting. And I'm going to define a notion that is also very heavily studied in extremal combinatorics, which is a complementary notion to Turán numbers. So the Ramsey number is kind of, it's not the opposite, but it's kind of a complementary notion to the extremal number. So it's the smallest integer n, so that all n vertex tournaments contain f as a subgraph. All right, so maybe I will just kind of set these two in contrast to each other. So usually when I ask for the extremal number of a subgraph f, I'm saying, what is the largest number of edges I can put into my subgraph so that there is some way of arranging the edges without getting a copy of f. Okay, so this gives me some number. And the Ramsey number is asking a totally different question. First of all, it's asking what is the smallest number of vertices, the Ramsey number of an oriented graph, so that no matter how you draw an n-vertex tournament, there will be some copy of f somewhere. And these are typically exponentially separated.
Definition of a tournament.
Pardon?
Definition of a tournament.
A tournament is just an oriented graph where every pair of vertices is connected by some edge. It's oriented either I to j or j to I. So it's like, you can think that like, unlike in a undirected graph setting where there's only one complete graph, right? There's only one way to connect all the pairs of vertices. In an oriented graph, there are like 2 to the n choose 2 if you label the vertices ways to connect them, right? Because for every pair of vertices in a tournament, I require there's some edge, but I don't place any requirement on which way the edge points. Other questions? Cool. So let me first start by making, some observations about how the Ramsey number is related to the extremal number. So I'll give you a proof idea for these two separate facts. The first is that the Ramsey number is not obvious it's finite from what I said originally. Maybe there's some like really, kind of fancy way to always find some tournament that does not have a copy of f. But it turns out not to be the case. And the reason is that so this is like a fact, I'm not going to prove now, but you can check that any tournament with 2 to the v of f vertices will have some transitive subtournament of size v of f. What that means is that suppose I have a tournament with 2 to the 6 vertices, 64 vertices, then within those 64 vertices, which are all connected by edges pointing in some directions, I can find 6 vertices so that there's some way to relabel the names of the vertices where all of the edges within the tournament amongst those 6 vertices go from smaller to bigger. Okay. The second observation is that by the definition of a Ramsey number, there is some F-free tournament on the Ramsey number minus 1 vertices. So if this is confusing, this is like the definition. This is just kind of like doing some munging with the definition of Ramsey number, because the Ramsey number is the smallest integer where all tournaments have a copy of F. If I subtract 1, there, has to be some tournament that does not contain a copy of F. Otherwise, the Ramsey number would be 1 smaller. So now if I combine these two observations, what I can do is I can get a lower bound by taking a tournament with the Ramsey number minus 1 vertices And I can replace each vertex in that tournament. I'll do a similar thing to the Turán construction. So if you remember in the Turán construction, if I want to avoid a 7-clique, I take a 6-partite graph that, a balanced 6-partite graph. And I'm going to do exactly the analog here, except that I have to preserve the directions. So I'm going to take a tournament on the Ramsey number -1 vertices. And then I'll replace every single vertex in that graph with like a clump of vertices. So now I have a bunch of clumps of vertices, and I will draw edges in a way that mirrors the original F-free tournament on the Ramsey number -1 vertices.
What is T of n r of -1?
Yeah, that's just like the number of edges in this graph I described, where we have n vertices and we like arrange them into R of f -1 parts and connect all the pairs of vertices that are in different parts to match the orientation here. That's why this is often called like the Turán number with these two parameters.
I understand.
Pardon?
I don't think I
Yeah,
understand
here,
that.
let me go back up to the figure because I think that will help a little bit in the undirected setting. So here on the right, we have T of 13, 4. So what do these two numbers mean? 13 means that the whole graph has 13 vertices. 4 means I'm going to divide it up into 4 parts equally and connect all the pairs of vertices in different parts. Do those two parameters make sense?
Yeah.
All right. So we're going to do the exact same thing. Cool. So we're going to do the exact same thing here. So now we have n vertices, and we're going to group them up as equally as we possibly can. Sorry, I don't know what's happening. Let me get this sorted. Can you all see my screen?
No.
No. Oh, right. Let me see if I can fix this. I have managed to disappear my slides. I think I have reappeared my slides. Let's try. Cool. Yeah, maybe can you all see my screen all right?
Yeah. Do you want to go
Cool.
into full screen mode?
I would love to if only I could make it work. I was trying to make this work for a while, but it does not appear to be working properly.
Okay.
Can you all see? Is it big enough?
Yeah, it's big.
Sorry, my computer is in the shop, unfortunately. So I'm trying to navigate with an iPad, which I would say is slightly suboptimal.
Okay,
So,
just go on.
all right, so let's kind of understand what this is saying. So what this is saying is now I have n vertices. That's what the first parameter of this t function is saying. And the second parameter is saying that I divide them up into R of f -1 different parts. Okay? So now I have these n vertices. I've clumped them up into RF -1 groups, and I'm going to connect every pair of vertices that are in different groups together. And since this is an oriented graph, I have to tell you one more fact, which is how do I decide which way to point them? And if for all of the vertices in one group and all of the vertices in another group, I'm going to connect kind of those pairs in the same way, and I'm going to copy the orientation of this F-free tournament on R of f -1 vertices. And so this function is just counting how many edges do I end up with in this structure. Does that make sense?
Yeah.
All right. So this gives me a lower bound. And why is it a lower bound? Because it gives me a construction of some oriented graph that actually does not have a copy of f. You can think of it as it is just a blow up. A good way to think about it, I don't think the numbers matter so much. If you don't even know, even if you don't know what a blow up is, like kind of formally, you can think of it as I just kind of enlarge the largest possible tournament that does not have a copy of F in a way that does not make it a tournament anymore, but kind of has still a lot of edges. I kind of like repeat every edge many times. However, I told you this was an equality, right? So we need a matching upper bound. And, the way we get a matching upper bound is by a very simple observation, which is suppose I had an oriented graph that had at least one more edge than this number. Now, we can just like forget about the fact that this graph is oriented. Let's just, for a moment, fully forget that this, graph is not oriented. And just imagine it's like an undirected graph. So if I had an undirected graph with this many edges, by Turán's theorem, right? By Turán's theorem, as an undirected graph, it would have to contain a complete graph on R of F vertices, which is some tournament, right? There's some actual orientation. We have no idea what the orientation is, but it's some orientation. But by the definition of R of F, whenever I have a tournament with that many vertices, I have a copy of F somewhere. So this is I think like kind of tricky because it involves like unpacking and repacking the definitions of these objects. But this kind of is what this is saying is kind of like the Ramsey number is like kind of really controlling in a very exact way when these directed acyclic graphs can and cannot appear.
The statement of the proposition should be the like EX sub O of N of F.
Yeah, it should be EX sub O, sorry. That's a typo. All right, so the kind of main goal of what we want to do is we want to control this Ramsey number. And it turns out that sometimes this Ramsey number, remember what the Ramsey number is? It's like how many vertices do I need such that no matter how like you draw a tournament for me and I will be able to find a copy of F in it for you. And there's been some previous work that shows that the compressibility of oriented graphs, which I think it's actually not very important for this talk what the exact definition is. So you just imagine it's like some property of these oriented graphs, which is there's been a lot of work trying to understand if this function takes the replacement, replaces chromatic number for oriented graphs. And there was some results that showed that basically it does. So kind of what the object that controls the Ramsey number of an oriented graph is compressibility, and it controls it in exactly kind of the same way as chromatic number does for undirected graphs. So you might say, oh, our work is done, but we actually really don't understand this notion or this quantity tau. Like it's more or less defined if you unpack the definitions to be the number that we would plug in that would replace chromatic number. Some observations or facts about compressibility are that it's at least as big as the maximum length of a directed path, like if I, kind of walk following arrows in F. And there's been, a bunch of work trying to study how is it related to the length of a directed path. I think there were people who thought that maybe like kind of the length of a directed path is really the thing that controls the Turán number or how many edges you can have without having a copy of F. I think that's been disproven because you can show that there are many examples of F where the compressibility can go like really, really, really much larger than the length of the largest path, even though sometimes it is just the length of the longest path. So I think here we kind of, although we have like kind of an answer in some sense, it's a pretty unsatisfying answer because it's in terms of a quantity that we understand very poorly. So there's a lot of work that we're trying to do to understand kind of what can we say about tau? Can we replace tau in some cases of F with something that's a little bit better understood? I actually think that like a lot of this work happened, in the 1900s, and I think there's not been a lot of active research on these problems. And I think that, there's a couple of new papers that come out now and again, including, at least one of these papers is quite recent. And I think that they're able to make a lot of progress on understanding these questions with relatively low-hanging fruit techniques. So I think there's like a lot of work to do to try and understand for specific families of F, can we say exactly how controlled or uncontrolled the extremal number is by kind of tau as a function of the length of the longest directed path? Is tau like a polynomial in that? Is it exactly the length of the path? When is it not? Can we just compute what the number is exactly for certain families without having this tau quantity that we have no idea what it is? Questions like that. But the, this is kind of where the story of oriented graphs has kind of ended in the present day for right now. This paper is actually very recent, one of the papers I cited. But I think there's like kind of two unsatisfying things about Turán problems and oriented graphs. The first is that we had to throw away any graphs that had directed cycles. But those oriented graphs are interesting, right? They also deserve to have a Turán number that's interesting. And so we should kind of think about what the right setting is to study them. The second is that our reason for studying oriented graphs and for studying graphs in general is, tied intimately to, purely theoretical reasons and applications in physics and chemistry, and also applications in the real world. And I think the most common example of a directed graph that people interact with are roads, where on roads, some of them are one way, but most of them are two-way. And, there's a mixed bag of which way you can go, but often between any pair of points, you can go both directions. And the kind of right graphical notion that captures those, I guess the names I've chosen here I think are the most common ones, but this is I think still not canonical, are directed graphs. So what is a directed graph and how is it related to an oriented graph? Well, a directed graph is just, where I allow between any two pairs of points, I can have up to two edges, right? I can have no edges between the pair. I can have an edge from like A to B. I can have an edge from B to A, or I can have both. And I think if you just imagine that, I have like, it's like a little bit of a street where, you might be able to go no ways. Maybe there's no way to connect these 2 points. Maybe there's a one-way road, or maybe there's a two-way road. You'll have the right kind of mentality. So all oriented graphs are valid directed graphs, but there are also some bonus directed graphs, right? Which are the ones which have, multiple edges, up to two. We're not going to allow more than two, up to two edges between every pair of vertices. And the next thing about directed graphs is that similar to undirected graphs, there's like a unique biggest one. And the unique biggest one is a fully complete graph, which is between every pair of vertices, I add both possible edges. So here you can see the fully complete triangle. Okay. And so already the story for directed graphs is like maybe much less satisfying. This is like the best summary I could come up with in the theorem, which is Brown, Erdős, and Simonovits showed that for every forbidden family of digraphs, there is some, I guess I wrote relatively simple, sequence of asymptotic extremal graphs. What does this mean? So first of all, what they gave is not explicit. What they basically said is that if you have some forbidden object, for example, suppose I forbid this fully complete digraph K3, there is some digraph in the world that has finite size. And if I take a blow-up of it, the similar way, kind of in a similar way to how I take blow-ups in the classical Turán problems, where I, replace every vertex with many vertices, then that sequence of graphs is the densest. However, there are much worse guarantees. For example, it might not be that all the parts are equal size the way that they are in the undirected setting. Needless to say, all this says is that there is some family of graphs that like asymptotically has as many edges as possible. And it's constructed from blowing up some finite object that one could, in theory, maybe compute, but it's not explicit. All right, so maybe this is like not a very satisfying starting point, but already you can see how much less is understood about Turán problems in directed graphs than about Turán problems in the classical undirected setting. There are some special cases where we do know the answers. So in 1970, Brown and Harari showed, you'll see this pattern looks very familiar. They showed that the extremal number of any tournament, so this is like if I take any tournament, any orientation of a graph where there's exactly one edge between every pair of points, then they all have the same extremal number. And the extremal number is formed by basically this, maybe I'll just say like, how do we get this object? Well, what we do is we divide up our n vertices into k parts, and then we put both edges between every pair of vertices in different parts. And that's how we get this answer. And it turns out to be the best that you can do, and it doesn't even matter how your tournament is oriented. So somehow this says that like the orientation doesn't matter at all.
Do we know like any cases where like the answer isn't of that form? Just wondering.
Yes, and I'm coming to those. But it's a good question. The answer is we know very, very little about directed Turán problems, and I think my biggest call for you all will be, if you're interested, I would really encourage people to explore these problems because I think they've been really underexplored since the 70s. even though I think they're really natural and like really basic questions. And like lots of very famous people worked on them in the 1900s, and then I guess people forgot sort of, or they became sad by this paper, which is basically unreadable. There's another result of Brown and Harari from 1970, which answers the question of what the Turán number is of a fully complete. So this notation, if you recall from my figure earlier, is this fully complete object where I have, this is like the unique biggest digraph. And here what I do is I take my, graph. I start with the transitive tournament on n vertices. So I number my vertices 1 to n. I draw all the edges in from left to right. And then I kind of group up my vertices into r-1 pieces. And for those pairs of vertices that are in different parts, I draw the backwards edges. So you can see this is also kind of philosophically, it's just kind of doing this undirected thing on top of like a base layer of a transitive tournament. So maybe this is also not very satisfying to the previous question because it's also basically orientation invariant construction. So now kind of once we have these kind of two results, let me tell you a little bit about kind of how they're proved, at least at a high level. So maybe if I have two digraphs, I'm going to let A, like I guess this bidirect B, be formed by drawing like all the possible edges in both directions between A and B. And the proof idea is that, this is like maybe also not a very satisfying proof idea, is you have to check the small cases separately. And then what we do is we show that if you check the small cases separately, you can do an induction argument. And that's kind of how this argument goes. I'm not going to go into it in more detail, but I think the kind of key that for you to take away is that there's some inductive approach once you've checked the small cases separately. And for this result about fully complete digraphs, it's exactly what I said earlier. Turán's theorem says if we what we can do is we can kind of think about, our directed graph in a slightly different context. What we can say is suppose we have some directed graph. Let's convert it to an undirected graph by saying that if between any two vertices there are two edges, we consider that to be an undirected edge. Otherwise, we pretend there's no edge. And if we do this, now we can try and kind of recast this problem as a problem about undirected graphs and apply regular Turán's theorem to this auxiliary undirected graph we constructed. Like I said, the proof details are not so important, but I think kind of the important takeaway is exactly the question that was asked, which is philosophically the way we prove this result is that we make an auxiliary undirected graph and apply Turán's theorem, which we do know about undirected because we understand undirected graphs very well, and we're able to then push that result back because this graph is so dense. Yeah. And this construction is exactly the one that I described earlier, which is we kind of have this base transitive tournament, and on top of that, we put a Turán graph that solves the undirected Turán problem for a clique on our vertices. Now, Brown and Harari also posed a conjecture. So one thing that's interesting about directed graphs is that there's lots and lots and lots of complete graphs. So what do I mean by complete? There are lots and lots and lots of directed graphs where between every pair of vertices, there's at least one edge. So there might be one, there might be two, we don't know which way it points, but tournaments have exactly one edge, and fully complete digraphs have exactly two edges, and there's a lot of in the middle. And so one question you can ask is, what can we say about the Turán numbers of these complete graphs that are kind of in between a tournament, which we do understand, and a fully complete digraph, which we also understand. And Brown and Harari in 1969 conjectured that the answer should be one of those two cases. You can, for every digraph in this intermediate state, it'll either kind of look like a fully complete digraph of some unknown size r, or it'll look like kind of the tournament of some unknown size, which might not be related. So the important thing here is this conjecture, while it looks very strong, is a little bit weak in the sense that the conjecture doesn't say that there's any relationship between R and D, which is how many parts we take in our construction and the size of this directed complete graph. Does the conjecture make sense to folks? So there was some follow-up work that, attempted to verify this conjecture for very small graphs and did. And what we do is we maybe start by verifying this conjecture is true for one family of complete graphs. So what is this family of complete graphs? This is where we start with a fully complete digraph, and we remove a certain number of pairs of edges, but we make sure that from every vertex, we remove at most one incident edge. And we show that if your complete graph is constructed this way, like by starting with something fully complete and then removing some disjoint edges, then this conjecture is true, and we even figure out which parameter it's true with. All right, so maybe that's like some good evidence for the conjecture. Unfortunately, you can also see, because my scrolling has gone, that this conjecture is actually false. And you can check that it's false because it doesn't hold for the digraph D formed by removing a 3 cycle from a fully complete 5-vertex graph. And we just compute what the extremal number is for this. We can do this using flag algebras, and there's also some analytic approach. Do I have a picture? Yeah, and so here is a picture of this digraph D. So we take a fully complete digraph on 5 edges, and we remove this red triple. And the construction to show that this is optimal is we kind of take three vertex transitive tournaments, like we get 3 blobs, we kind of connect them bidirectionally, and this is kind of the best possible construction. So this is, I guess, somewhat surprising that kind of this conjecture, which was believed to hold for quite a long time, is false. We have a modified conjecture, which is like somewhat weaker. It's a little bit complicated to state, but we really know very, very little about these Turán numbers. So mostly what I've talked about for directed graphs are really, really dense things: tournaments, complete graphs, fully complete graphs. We can ask also, like, what do we know about, much sparser things? Like, how many edges can you have in a directed graph before you get a path of a certain length? And for directed paths, first I'll say Turán numbers for directed graphs are like almost all unknown, in contrast to the undirected setting. And I really think it's very exciting to try and make progress studying these, and because I expect like there to be a lot of low-hanging fruit. So Faudré and Shelp. So what I'm going to do now is I'll just take the next couple of minutes to highlight a couple of the results that we do know, which is really like I think summarizing almost every result that we know, and contrast what is true in the directed setting with what is true in the undirected setting. So Faudré and Shelp showed that if we want an undirected graph, so if I have an arrow, it's directed, and if I don't have an arrow, it's undirected, then the most number of edges we can have without getting a path is linear. Joe and Lee in 2021, however, and in fact, I wrote something weaker. They give a very precise statement of how many edges a graph can have without having a directed path of length k plus 1. And this is also kind of controlled by this compressibility notion that was discussed earlier, because for very sparse graphs, Turán numbers and oriented graphs and directed graphs are very related, although there's no black box relationship known between them for most classes of forbidden structures. Oh, I guess here I do have a definition of transitive graphs. So this is one notion, which is that if I have, 2 edges, then I have to have this third edge that is in the graph, and the opposite direction cannot happen. So like we discussed earlier, transitive digraphs cannot have directed cycles, and they cannot have anti-parallel edges. And the proof of this result kind of goes by considering some transitive orientation of our favorite undirected k-partite, k groups of vertices, all balanced and connected. And then the upper bound, they're able to kind of split up the graph. So the upper bound, what they do is they break up their best possible construction into the pairs of vertices that have 1 edge and the pairs of vertices that have 2 edges. And they're able to analyze those. So I think the details are not super important, but they're able to then kind of split these up and treat them separately and show the upper bound that matches the lower bound construction. We also understand the Turán number of orientations of trees. In 1970, Graham showed that if a tree has no length 2 directed path, then its oriented Turán number is linear. Trees are all bipartite, so in fact we know that their undirected Turán numbers are also very small. And you can generalize this to show that this holds kind of in more generality than just length 2 directed paths. I'm going to skip the proof idea in the interest of time. But maybe the last example I want to cover are directed cycles. So in the undirected setting, if you recall earlier, triangles and squares had very different behavior, right? If we want to forbid a triangle, we can have up to n squared over 4 edges. Whereas if we want to forbid a square, if you remember that we can only have up to n to the 3/2 edges. And in fact, we know all of the Turán numbers of all the odd cycles and none of the even cycles, basically. So Joe and Lee in 2021 gave like an exact characterization for the Turán number of a directed cycle. And maybe the only thing I'll call your attention to here is that here there's no the difference between odd and even doesn't really matter very much at all. And we're able to show kind of some generalization of this, which is for all orientations of cycles, where if I have a cycle and I can make the edges go any which way, not just necessarily all going in a loop, and you get some kind of very peculiar structure where you get different cases depending on like, what these AIs say is like you go forward for like 3 edges and then the arrows go backward for 2 edges, then forward for 5 edges, then backward for 6 edges. And depending on kind of the properties of these numbers, you get kind of very different results with associated very different constructions of best possible dense digraphs that lack these funny orientations of cycles. All right, so there's like some other examples that you can have, but maybe kind of the main thing that I want you to take away are that there's like a lot of open questions in a lot of areas of Turán problems. So I think hypergraph Turán problems and bipartite Turán problems that I mentioned at the beginning have gotten like a lot of attention. But I think that these problems are really basic. They've been studied by the same, people who started the field and who thought they were really interesting problems. They're very fundamental, not just because of applications, but also because I think they're really basic questions. And we understand them incredibly poorly, and there's a lot of room to kind of make progress with relatively low-hanging methods compared to the ones that are being deployed for other Turán problems. And so I'm going to leave you all with a few questions and conjectures, but that's all that I have. Thank you so much.
Okay, thanks for a great talk. So are there any questions now?
So I don't, so like, what's like, do you know anything about like Turing problems on like typical graphs or like Ramsey numbers, whatever? Like,
Turing problems on, pardon?
like if you choose a graph like randomly, what do you expect its Turing number
Yeah, you can study this question. So this has been studied for graphs and is known. I think there's like a line of very beautiful work on it. I think it is naturally much less studied than directed setting because everything is. But I think even kind of getting good asymptotics and understanding the distribution of Turing numbers for like random graphs or Turing numbers in random graphs and of random graphs, both of which are separate questions that are interesting, is still pretty recent. There's like a paper by Sam Spiro for the last couple of years that studies Turing problems in random graphs. So I pick like a triangle and I ask, how long will it take a triangle to appear in a random graph?
Oh, that's cool.
Which is also interesting.
Thanks.
Mm-hmm.
Are there any other questions at the moment? Okay, if not, then let's thank Nitya again, and then we'll move on to the next section of the quiz.